So let's look at limiting reactants and percent yield. So limiting reactant deals with situations where in a chemical reaction, your reactants are not mixed with a proper mole-to-mole ratio. So one or two of the reactants can be in excess. Now, obviously, we always want to use our reactant in a stoichiometric ratios for many reasons. But at the same time, oftentimes we need to use one or two of the reactants in excess amount just to control the direction of the reaction. So if we want our reaction to go to completion, go all the way towards the product, oftentimes we need to use one of the reactants in excess. That's one of the reasons why sometimes your reactants do not have the proper mole-to-mole ratio. So in this lecture, we want to learn if our reactants are not in a stoichiometric ratio meaning that if they don't have the proper mole-to-mole ratio, how can we still find the amount of product that's going to be produced? So before we start by actual chemical equation, I want to show you the example here. So based on this example, we want to learn a couple of terms, and then we will expand this to chemical equation. So let's say you're looking at a process of making bicycles, like functional bicycles, and for this you're given 8 wheels, 4 frames, and 3 pedal assemblies. And you're asked to put this together and make bicycles. And keep in mind that to make each bicycle, you're gonna need 1 frame, 2 wheels, and 1 pedal assembly, so your bicycle is actually functional. So with the number of pieces or parts that are given to you, the maximum number of bicycles that you can make is 3. And after you're done with making the bicycles, 3 functional ones, you're gonna end up with 1 frame and 2 wheels that are left over. And I can't make any more bicycle because I still need 1 more pedal assembly to make a functional bicycle. So let's write this in a different way. So we started with 8 wheels. And we had 4 frames. And 3 pedal assemblies. And our goal was to make bicycles. We want to know how many bicycles we could make. So there are a couple of ways that I can predict the number of functional bicycles that I can make here. So I want to show you how I can predict the number of bicycles that could be made based on what's given to me. So one way of doing this is by looking at each one of our starting material, which are wheels, frames, and pedals. So if you have 8 wheels, the maximum number of bicycles you can make is 4 bicycles. If I have 4 frames and I'm looking at each one of these parts individually, so if I use all 4 frames that's given to me, the maximum number of bicycles I can make is also 4 bicycles. Now, with only 3 pedals, the maximum number of bicycles that I can make is only 3. So what I did was that based on the number of pieces or parts that I was given, I found out the maximum number of bicycles that I could make. Now, when I look at the number of bicycles that I can make with each one of those parts, as you can see, they don't all give me the same number of bicycles. With wheels and frames, you can make 4 bicycles, whereas with 3 pedals, you can only make 3 bicycles. Now, how do I interpret this? Just the fact that I don't end up with the same number of bicycles tells me that I don't have the proper ratio in between wheels, frames, and pedals. If I did have the proper ratio, appropriate number or amount of each one of these parts, I would have ended up with same number of bicycles. But just the fact that I don't end up with the same number of bicycles, it tells me that I have less number of parts that I need. One of the parts, I don't have enough of it. So the part that gives you the fewest number of bicycles is the part that's going to run out. It's the part that's going to control the number of bicycles you can make. Or in other words, it's the part that's going to limit the number of bicycles you can make. So that part is going to be the pedal assemblies. So since the pedals give you the fewest number of bicycles you can make, it means that we don't have enough of pedals to make more bicycles. So the number of bicycles you can make is limited by the number of pedals you have available. So pedals is going to be your limiting part in this process, or limiting piece in this process. Why? Because it's limiting, it's controlling the number of bicycles you can make. Now, since pedal assembly, we don't have enough of it, it's our limiting part, it means that frames and wheels are in excess. Now, one other important thing here is the number of bicycles we can make. The maximum number of bicycles you can make is going to be 3 bicycles max, because as soon as you run out of pedal assemblies, you can't make any more bicycles. So the number of bicycles that you can make is totally controlled or limited by your limiting part, which is the pedal assemblies. So we're going to use the same concept for chemical equations. So we're going to look at our reactants, the number of moles of each reactant, see how many moles of products you can get. Now, if we end up with the same number of products, same number of moles of products, it means that all of our reactants are in a stoichiometric or proper mole-to-mole ratio. If they don't give us the same number of products, it means that one is limiting and one is excess. So let's do a couple of examples and practice a little bit more on the limiting excess concept here. So you're looking at a combination reaction of hydrogen and chlorine gas that gives you hydrochloric acid. So you start with 5 molecules of hydrogen and 3 molecules of Cl2. So you have 5 molecules of hydrogen gas and 3 molecules of chlorine gas. And you want to know how many molecules of hydrochloric acid you can make. Now, anytime that the initial quantity of all reactants are given to you, you have to check for limiting excess, meaning that you want to find out the amount of product that's going to be produced and then see if your reactants are in a stoichiometric ratio or one is limiting. So what I would do is that from 5 molecules of H2, based on the balance equation, I know that I would expect to get 10 molecules of HCl. Now, for that 3 molecules of Cl2, I would expect only 6 molecules of HCl. So based on the initial quantity of the reactants, I found out how much product I could get. Now, just the fact that I don't end up with the same number of HCl molecules tells me that one reactant here is limiting, the other one is excess. Now, the reactant that gives you the fewest number of hydrochloric acid molecules is going to be your limiting reactant. So what I interpret from this is that Cl2 is my limiting reactant, and hydrogen is my excess reactant. So now, since chlorine is the limiting reactant here, it means that the number or the maximum number of hydrochloric acid molecules that can be produced is totally limited by chlorine. So since Cl2 is the limiting reactant, therefore the maximum number of hydrochloric acid molecules we can make is 6 molecules of hydrochloric acid. So this 6 molecule of hydrochloric acid, can call it different things. I can call this is the expected amount, or I can call this maximum amount. So these are the different ways that we can word this. Or I can also call this the theoretical yield. So, from a reaction of 5 molecules of hydrogen gas, 3 molecules of Cl2, I know that the maximum number of HCl molecules that I can make is 6 molecules. So, if I have in my reaction flask 5 H2 molecules and 3 Cl2 molecules, after they react with each other, what I would expect in my reaction flask is 6 HCl molecules. And what else would I expect to see in this flask after the reaction is done? I would expect to see some leftover hydrogen gas too, because remember, hydrogen gas we had excess of. So I would expect to see some leftover hydrogen gas. Why? Because hydrogen is the excess reactant. And I can also figure out how much of hydrogen gas is left over here. You know, the ratio between hydrogen and chlorine is 1:1. So for 3 molecules of Cl2, you only need 3 molecules of H2 as well. And that leftover H2 is 2 molecules of H2. So we have a good understanding of exactly what we have in our reaction flask. So we have some product, which is hydrochloric acid, but I also have some leftover reactant because hydrogen gas was in excess and some of it was unreacted. So you call it leftover or unreacted. So this is what our strategy is going to be to solve for limiting excess problems. So when the initial quantities of all reactants are given to you, the first thing you want to do, you want to find the amount of product that's going to be produced. Now, after you find the amount of product that's going to be produced based on each reactant, then you want to look at the amount of products. If it all gives you the same amount of product, it means that your reactant had the proper mole-to-mole ratio. If not, it tells us that one reactant is limiting, the rest of the reactants are in excess. And keep in mind that the maximum amount of product that can be produced, or your theoretical yield, depends on your limiting reactant. So you use the limiting reactant to find out the maximum amount of product that's going to be produced. So let's do a couple of examples here. You want to know how many moles of hydrochloric acid can be produced from 4 moles of hydrogen and 3.5 moles of chlorine. What is the limiting reactant? So first of all, we gotta make sure that the reaction is balanced. It is balanced. And now, since the initial quantity of both reactants are given to me, I gotta solve for limiting excess. So what I'm gonna do is that from moles of H2, so from moles of H2, I'm going to find moles of HCl. And then from moles of Cl2, I'm also going to find moles of hydrochloric acid, which is my product. And then I'm going to compare them. So this is my plan. So let's do it. We have 4 moles of H2. And based on the balanced reaction, each mole H2 gives us 2 moles of hydrochloric acid, which is 8 moles of hydrochloric acid. So what this means is that if I use 4 moles of hydrogen gas completely, the maximum amount of hydrochloric acid I would expect to get is 8 moles. Now, if we use 3.5 moles of Cl2 completely, we would expect to get 7 moles of hydrochloric acid. Now, based on these calculations, I know that hydrogen and chlorine are not in a stoichiometric ratio because they don't give me the same amount of hydrochloric acid. So from here, what I interpret is that Cl2 is the limiting reactant. And if Cl2 is the limiting reactant, it means that H2 is in excess. Now, we still have to answer the question. It says how many moles of hydrochloric acid can be produced. So I say the maximum number of hydrochloric acid that can be produced is 7 moles of hydrochloric acid. So you can either write it as 7 moles is the theoretical yield or expected, or you can box this 7 mole here. Now, if you don't box anything, or if you box both answers, it's not acceptable. Because the question is asking how many moles of hydrochloric acid. You have to clearly indicate the maximum number of hydrochloric acid that you can get based on your limiting reactant. How many moles of Fe3O4 can be produced from 16.8 grams of iron and 10.0 grams of water? And what is the limiting reactant? So this is how you want to approach this. Since the initial quantity of both reactants are given to you, you want to check for limiting excess, meaning that from mass of iron, you want to find moles of iron, and then moles of Fe3O4. And then from mass of water, you do the same thing too, and then compare the amount of product. So let's start with 16.8 grams of iron. So 16.8 grams of iron. We're going to convert this to moles of iron first. Each mole iron is 55.85 grams of iron. And then based on the balanced reaction, each 3 moles of iron gives us 1 mole of Fe3O4. Which is 0.100 moles of Fe3O4. Now we do the same thing with water too. We have 10 grams of H2O. Each mole H2O is 18 grams of H2O. And based on the balanced reaction, each 4 moles H2O gives us 1 mole of Fe3O4. Which is 0.139 moles of Fe3O4. Now, since I don't end up with the same amount of Fe3O4, it tells me that one of the reactants is limiting and the other one is excess. So the reactant that gives you the fewest amount of product is going to be your limiting reactant. Therefore, based on this calculation, I know that iron is the limiting reactant. And since iron is the limiting reactant, it means that H2O is in excess. So the maximum amount of Fe3O4 that I would expect to get is 0.100 moles of Fe3O4. So how many grams of barium sulfate can be produced from 200 grams of barium nitrate and 100 grams of sodium sulfate? So let's first find out if any of the reactants is in excess or not. So starting from 200 grams of barium nitrate, we want to find out the amount of barium sulfate that's going to be produced. So I'm going to convert to moles of barium nitrate first. So this gives me 0.7651 mole of barium sulfate. Then we're gonna do the same thing with sodium sulfate too. So 100 gram sodium sulfate. Each mole sodium sulfate is 142 grams. So from 100 grams of sodium sulfate, we expect to get 0.7042 moles of barium sulfate. Now this tells me that barium sulfate, you don't get the exact same amount of barium sulfate, so this tells me that sodium sulfate is the limiting reactant here. So the maximum amount of barium sulfate I would expect to get is 0.7042 moles of barium sulfate. Now the question is asking for the mass of barium sulfate, so we're gonna do one extra step to convert from moles of barium sulfate to mass of barium sulfate. So we expect to get 0.7042 moles of barium sulfate. And to find the mass, you just have to use the molar mass of barium sulfate, which is 233.4 grams of barium sulfate. So we would expect to get 164.4 grams of barium sulfate, which is our theoretical yield or the maximum amount of barium sulfate that can be produced.